All right, this is Element Rescue. We are going to start a series which kind of breaks down micro portions of a system. We believe by breaking down various processes within a system, like a Hall system, lower system, rappel system, etc., the end user will be able to gain a much better fidelity on the micro processes that exist within that system, which gives you the ability to also enhance your capability for improvisation. So for today, on this micro session, we're going to take a look at the Capstan equation for belt friction and how that relates to descent control devices. We're going to use Attaway's 1999 paper for this one. His paper goes into much greater depth of the role friction plays within various angle and deflection from edges to DCDs and a whole bunch more equations than we're going to get into. But for that, we're going to look at this. He presented this in 1999 at an IDERS conference. The paper is phenomenal also, which we'll put onto our website for you to be able to click and see that PDF. In the end, those conclusions, after doing a bunch of this work, was that using the simple friction law leads us to conclude that the frictional forces for a rope depends only on three things. The tension that's within that rope, which is kind of your weight, the load value as far as with gravity and things like that, the coefficient of friction, and the total angle of contact. We are going to dive into the munter hitch. We use the munter hitch for a bunch of things from emergency egresses to just regular rappelling to lowering casualties, manipulating it for various systems from a one-way munter to a 1.5, a monster munter, etc. There's a lot of variations of this. So we're going to look at a simple munter today. With that, realize we're only going to be looking at the static coefficient of friction. So that is how much force needs to be applied to the brake strand to keep you from moving. So just in a holding type of position, whether you are braking that casualty or that person that you're lowering off and just holding them statically, or if you're using it as a rappel device. The equipment we used was a 7.8 millimeter aramid sheath nylon core semi-new rope, a 7075 aluminum HMS carabiner, which has an 11.9 millimeter rope bearing radius, which is obviously this distance that exists here on the bottom part of the carabiner where the rope or the webbing is going to articulate with, a hanging crane weight scale that goes up to 1,100 pounds, and a Rock Exotica enforcer. We also made this is, you can just click on this and download this also as a PNG. This is a 360-degree protractor, which makes really trying to estimate these angles a lot easier. We're products of Southern Education, so we try and keep it as simple as possible. In the end, we have to determine each angle present where the cord goes around that carabiner. Sometimes the cord will touch its cord, which is the case in the munter hitch. So this is a transparent PNG that you can download. You can take pictures on your phone or whatever, put it into a PowerPoint, slide this protractor in over that, resize it, and you'll see kind of how we did that, and you'll be able to guesstimate your angles in each position. So starting off, angle number one, we took the brake strand on this one, and you'll see we resized this protractor to basically right around the center, and this picture is slightly canted, but resize it to where we found kind of the center, and we're looking at the center, which would be on that carabiner and the rope there. So we estimated this one at 275, so we'll show you how we did that real quick. So when we enlarged this, we kind of highlighted it with bright green there. So we lined up the 0 angle with the first point of contact of that rope around the carabiner, and then we basically just follow that rope around. So we're going clockwise on this one as it loops around, and then where it stops touching. So when we take that green line out, we'll find it's kind of right in between that 270, 280. We may just be slightly, very small off there, but this is in reality a little bit of ghetto type of research here. So we're estimating that at 275. When we go on, we'll go to that second angle, which will be the load side. So we got the load side coming in right here. And we just did the same thing. We estimated this one at 330. So when we enlarge that up, we'll see we kind of rotated this. It's a free rotation as a PNG within your PowerPoint. kind of spin that around to where we hit our first point of contact coming in off that load strand. And once again, we just kind of followed that rope around clockwise to where we lost contact with it. So we estimated at 330. You can see that it's slightly a little to the left, so maybe 332, 333. We went with 330 on this one. And then our third angle is actually going to be the rope contacting the rope, which kind of is able to cinch that in. We estimated this at 130, so let's take a look at this real quick. There's our 0, lined it up. That's right where this rope starts to contact in here, and we work that around counterclockwise. So we're going to be on the other part of our projector, going from the red portion counterclockwise, and found that this is about the area right in here that we lose contact, which is almost exactly at 130 for the equipment that we were using. One person also mentioned the fact that we do gain a little bit of a coefficient of friction with our brake strand on here. No, for our study we didn't. We had a hanging weight of about 180 pounds on this. This would be potentially playing more of a role if we were actually measuring how much force it took to lower them in a more dynamic fashion. So it doesn't really play a role in what we're looking at today. So now that we got all of our angles, now it's time to plug them into an equation. So putting it all together, we add the angles together. So we're just going to work this out on the side a little bit so you can kind of see that. We use this app. It's a free app. It's a scientific calculator. The one thing we're looking at on this to make our life easy is the Euler's constant, which is right there. So that's what we're looking for on the scientific calculator. It's a free app at the App Store. So we want to go through and add these together. So we take 275 plus 330 plus 130, which will give us around 735 degrees. We need to now convert this to degrees, the radians pi. So to do that, pretty simple, just divide that number by 180 and we get 4.0833 pi radians. Now we're going to need to take pi out of that, but that's actually going to come down here when we get into the equation. The second part of this is probably one of the more frustrating or critical aspects of this, is estimating what the coefficient of friction is. We have a slide on this here in a second. We'll talk about it on all the things that can affect your coefficient of friction. We estimated it at 0.25. I believe that's what Attaway did in his paper also. We've seen kind of a whole array of things. You can pull up coefficient of friction numbers for steel, for aluminum, for things like that. Really difficult to estimate this because there's so many variables based on the condition of your rope. Is it wet? Is it muddy? All those type of things. So we went with 0.25. It's just kind of that estimation. We'll show you kind of how you can derive that here in a second. So that is for a semi-new 7.5, 7.8 millimeter aramid rope with a 70-75 aluminum carabiner. Now we take these numbers and we plug them into the Capstan equation for belt friction. So that's basically, in a nutshell, it breaks down to this, where we have our force or our tension, Euler's constant, which is listed down here at 2.71828, and a lot of numbers, our coefficient of friction, which is there, and then this is going to be our total angles of contact. So when we do this, we're going to move down to section 5 here, right down here. This is what it looks like. So we take that number 4.083 and we go ahead and get rid of pi by timesing that by 3.14. That gives us 12.821. Now we go, and since we're always remember doing parentheticals first, so we finish this up. So we got that one nailed down. Now we need to times that by what our coefficient of friction is. So that's just take that number times 0.25, and that will give us 3.205, which we have right here. And now comes the Euler's constant. So that 3.205 is an exponent. That's why when we change a little bit within our coefficient of friction, it actually makes a pretty large difference in the outcome of the number that we get. So at that point, we just have this number. We go over to this portion here, which has the exponent, which we already have in there, to Euler's constant. Press that button, and that's where we get 24.66. So basically, we can estimate that we have about a 24-to-1 holding power, saying that if you're 240 pounds or your load is 240 pounds, you'll need to input right around 10 pounds of force on that brake strand to be able to keep that load static without moving. Moving on. So the variables, we kind of talked about those variables. There's a bunch of them. So coefficient of friction is a bit difficult to predict. As we mentioned before, it does make an exponential difference. So as you're doing your equations, go ahead and up or down by 0.5 and you'll see a huge difference if you go up to a 3 as your coefficient of friction, or if you move down to 2. So it's something to be thoughtful of. Things that influence it: rope, your condition of your rope. Is it muddy? Is it wet? Is it old? Is it new? What kind of material is your rope made out of? Is it an aramid from the aramid family, a Technora, Kevlar AP, Kevlar K29, a Tworon? Is it a polyester? And obviously the condition that it's in, and then the properties of it. Is it a stiffer rope? Is it more malleable? Your hardware, same type of thing. Are you dealing with what kind of alloy of aluminum are you dealing with? Is it steel? Those will all affect your coefficient of friction at that microscopic level that makes a big deal. In the end, see what you come up with based on what your calculations are with the equations and what you're estimating your coefficient of friction at. I would say start at 0.25 and go from there. But you can test your equation by just taking a scale like we use with our crane scale and weigh your load. So take somebody and free hang them on that and see what their weight is. Then turn around and put them on one side of a munter hitch, create a high anchor, and put a munter on there. Have them elevated on, and then just have them lower themselves onto your weight, and you just kind of counterbalance that. And we kind of kept one hand on that munter and just basically found where that tipping point was, where we were able to hold them with the lightest weight possible before we started feeling the movement of the rope in the munter hitch with our hand, and take that calculation and see where you come out with, and see kind of what you're doing, and then switch your material, switch your rope, switch your carabiner types from a steel to an aluminum, and see how that works. And really in the end, it's just a balance of inequalities. So obviously this is our load strand within our munter, signified red, where the most tension is, and you can see as that comes in and we have the first interface of an angle, we start taking some of that load off, and as that makes its full rotation around that carabiner, we start losing the tension that's within that munter hitch. And as we come back up over here, it's to the brake strand where we're really not holding too much of that weight. So whether you're dealing with a clove or a munter, it's always kind of where's that balance of the inequalities that exist between your load and what you're holding. So we found this online. The bottom ones are from Steve Attaway's paper. The top one we thought was kind of interesting. So if we look at this, it's a picture that shows, hey, we got 2,000 pounds of force here. We do 3 circles around this pole. They give us the coefficient of friction as being 0.3, and it basically states that we only need 7 pounds of force on our end to hold 2,000 pounds, and that 2,000 pounds is dispersed through those angles of contact. So when we want to check that, we can actually just plug that into the equation we just did. The estimated angles are obviously 360 degrees, which gives us 1080. We go ahead and divide that by 180 and get 6 degrees radian. Then we go through and we get pi out of there, and we times that by the coefficient of friction that they gave us, which was 0.3, and that gives us this number down here, which is 5.652, and put that as the exponent to Euler's constant, we get 284.8606. And when we look at that, we take that by 2,000, we realize that the answer is actually 7.02. So that's where we get our 7 pounds of force on our end for holding, compared to the 2,000 pounds of force or weight that we have on the other end of that. Attaway did some pretty cool stuff with a brake rack, with a bar rack here, showing the different configurations of it being in a loose configuration, where he estimated those degrees of contact at 105, and plugged that into the equation and got a 12-to-1 holding power. But when we look over here farthest to the left, we see that that's where he kind of crammed those bars together, creating the highest friction point, which increased it to about 120 on each one of those, with a terminal at 80 and a beginning at 240, where we can really crank that brake on, and it jumped up to a 31-to-1 on that equation. If we kind of fly over here and we drop one of our bars here, then we can see that goes down significantly to a basically a 4-to-1 as far as that goes, which shows you the importance of being able to add that on if you had a couple 100-foot rappel. I believe there's a case not too long ago in Yosemite where one of the guys were going off the top, and because of the huge amount of weight of that rope below them, rocked it down to just a couple bars to get them going and was never able to gain any more friction in there, and that basically got out of control and they ended up spiraling down to their death. When we look at the 8, which is kind of cool, a lot of us at one point in our career still maybe do use a rescue 8. So you can see in that open non-brake position, we're getting right around a 10.5 to 1 on the holding power just from those angles that come through there. But when we throw it down into a brake position, we gain that extra 270 right here, which then equates out to about a 15.6 to 1 on the holding power. So when we look at this, back to the munter, there's going to come times where that munter may not cut it for you. So if you're using that as an egress capability, or you're lowering more than one person down on that rope, depending on your equipment, you may need a little bit more friction. A lot of people may jump to the monster munter. We don't really use it too much. We've done some stuff where we've had 600 plus pounds on the end of that and still found ourselves having to feed rope into that munter hitch to get it going. So it definitely wasn't the smoothest one. It provides an enormous amount of friction, but where's that kind of happy medium? So we were doing a munter 1.5 for a while, which I think even if I was doing an anchor and lowering somebody down or lowering a couple people down, it's a pretty good route to go. We have a video on that if you're not familiar with it. But what we found is we were looking at Black Diamond's little study that they did on ATCs by adding a second carabiner into your belay loop on an ATC and the friction that adds. We just jumped in and did kind of the same thing with an ad hoc little study. So we were hanging kind of between 135 up to about 215 pounds on a munter hitch, and we were just hanging that as if we were going to rappel off that, put a T-block or a prusik on the brake hand stride and put the scale on there just to see where that tipping point was of where we're holding the least amount. And then we added a second carabiner in there and found that, for instance, if it was taking 16 pounds of force to hold us statically, just not moving whatsoever on a munter hitch, just free hanging, as soon as we added that second carabiner, on average, it would only take, in that case, maybe 8 pounds of force to be able to hold us. So it added quite a bit of friction to it, which made it real nice. You can see in the picture here how we rigged that is we just did opposing gates. And we didn't do opposing gates for a safety issue. We did opposing gates because the carabiners would sit flat against each other, to where if we had both these gates on one side, it would create a gap right in that area. So it doesn't make a difference, not really sure. We just kind of did it a little bit cleaner, and it rolled out pretty nice for us. So if we're doing an emergency egress, we know we're wearing a bunch of kit, just adding that second carabiner in there may make the difference for you, to where you can have a much more controlled, smoother descent on that. So that is it. That is the Capstan equation as it applies to belt friction and descent control devices. So try it on what you got. Let us know how it rolled, and we'll see you next time.